Okay, so for this week, we are looking at chi-squared tests. Chi-squared, chi is Greek letter chi. It looks kind of like a script capital X squared. And there are a couple of types of chi-squared tests we're going to look at. One is goodness of fit. And what goodness of fit is we're testing a prediction or a statement of a standard of how things are divided or distributed. One example would be M&Ms. You figure out, you look at the M&Ms company says that 10% of the M&Ms are yellow, 20% are brown, 30% are blue, 20% are red, and so on. And you can actually look through then a couple of bags of M&Ms and count them and see if those proportions match up. That's goodness of fit. And then there's test of independence. In independence, we're looking at two variables applied to the same set of data. And see if the value or the result of one variable has an effect or alters the distribution of the other variable. So let's go ahead and we'll start out here looking at goodness of fit. So first thing we're going to do, we're going to find critical values of chi-squared distribution. We'll be able to find that with the calculator or with tables. Then we're going to actually perform the goodness of fit test. So our critical values. First, we got to look at what the chi-squared distribution looks at. The chi-squared distribution is not symmetrical. So far, the normal distribution and the t-distribution are both symmetrical, that bell-shaped curve. The chi-squared distribution is skewed. In fact, just like the t-distribution, it depends on degrees of freedom. You can see here that for 1 degree of freedom, it is actually a single curve. It's not even a hump. And then as we get to 2 degrees of freedom, or 5 degrees of freedom, it gets a hump with that long tail skewed out to the left. And at 20 degrees of freedom, it's starting to almost look symmetrical. So the higher the degrees of freedom gets, the closer it is to becoming a symmetrical curve. So we have those different curves. Since it's not symmetrical, the chi-squared statistic are always greater than 0. We never have negative values. The chi-squared distribution starts at 0 and goes up from there. So here in this table, we're looking at alpha. For chi-squared, we always reject on the upper tail. You can see up here is where we will reject. So the rejection rule will always be that we reject the null hypothesis if chi-squared is larger than the critical value. So to find that critical value, we look at alpha, which is our level of significance. 0.05 here, so we're looking at the table here, that's 0.05. If it's 12 degrees of freedom, so in other words, we've got a sample of 13 items, 12 degrees of freedom, and we gotta be careful. The chi-squared degrees of freedom can be worked a couple of different ways. But for 12 degrees of freedom, alpha of 0.05, the value of that critical value is 21.026. So you can see here that says 21.026. It's kind of small print, but that's our critical value. So for this test, we would reject the null hypothesis if the chi-squared value, if our test statistic was above 21.026. Of course, we need to know what those hypotheses are, and that's going to start right now as we perform that goodness of fit test. So again, the goodness of fit is looking at predicted values versus observed values. So here we want to look at, we're testing a die to determine if it's fair. So there's no actual prediction given here, but if we're trying to determine if the die is fair, the assumption is that each number is equally likely to occur. So the outcomes are equally likely. 1, 2, 3, 4, 5, 6. So that would say is the predicted value or expected value is going to be the same for each of these. And what we would do then is we just look at the total number of rolls and divide it up equally amongst those different possibilities. So the Gambo rolls the die 60 times, and he counts how many times each value comes up. And we have that table down here. These are what we call the observed frequencies. This is what actually happens. So this is the actual data. From the events that we observed. Next, we got to figure out what those predicted frequencies are. And as I said before, the prediction, if the die is fair, is that they're all the same. And that actually becomes our null hypothesis in this case, is that all those proportions are the same, so each 1/6. So the null hypothesis is that they're 1/6. The alternative hypothesis is going to state that not all of them are equal, or at least one of them is different. And that's generally the way we word the alternative, is at least one is different. Or at least one is not the 1/6 or 0.167. So now then we need to actually find the expected frequencies, which is based off that expected proportion, the 1/6 times the total value, the total size of the sample n. We rolled the die 60 times, so each frequency would be 60 times 1/6, or 10. So each of those values had an expected frequency of 10. Now here they were equally likely. We expected them to all to happen equally, so that's why we did 1/6 to get the same number for all of them. If we had different proportions or different percents, like with the M&M's example where Mars claims that only 10% are yellow and 20%, or 10% are brown and 20% are yellow and so on, we would take that total times that percent and divide it up by those percents. We'll see an example of that later on here. So here's our hypotheses. Again, the null hypothesis is that each of those proportions equals 1/6. And the alternative is that at least one is different. Our expected value for each is 10. So we arrange our table like this. We have those observed values that we observed earlier right here. And these are the expected values that we just calculated. So if it's true, the difference between the observed and the expected will be not significantly large. It'll be small enough to be statistically not significant. To calculate our test statistic then, it's always going to be the observed minus the expected squared, then divided by the expected value. So let's go back up here. For rolling a 1, it's observed as 12 minus the expected of 10. That difference is going to be squared and divided by the expected value. Well, 12 minus 10 is 2. 2 squared is 4. 4 divided by 10 is 0.4. So the value for 1 is 0.4. Now we're going to do the same thing for 2, 3, 4, 5, and 6. We're going to get all of those values of the chi-squared statistic. And the overall chi-squared test statistic is found by adding them all up. So that's how we find the test statistics. Let's look at the rest of our calculation here. So this is our hypothesis testing process. We state the hypotheses, which we've done. We found and compute the expected frequencies and put that into the table. Be sure that all of them are 5 or more. We can't have expected frequencies that are less than 5. And we did. They're all 10, so we're good there. The significance level we chose here was 0.05. That was alpha. Now we have not found the critical value yet. We're going to find that here in just a second. Now then we would compute the test statistic and then compare that to the critical value and state our conclusion. So we have 6 categories here. That's our observed. We just set up the table a little differently here. Put the expected on the end. This is just their way of arranging it so they can do their calculation. So then we did observed minus expected. So 12 minus 10 is 2. 2 squared divided by the expected of 10. That's the 0.4 that we calculated before. 7 minus 10 is -3, squared is 9, divided by the expected of 10 is 0.9. And we just follow down. 14 minus 10 is 4, squared is 16, divided by 10 is 1.6. And we get all these values, we add them all up, we get a 9.4 is our test statistic. Now our critical value, we have 6 categories, 1 through 6. So our degrees of freedom are 6 minus 1, or 5. So we're going to look in the table to find that. Now I'm just going to scroll back up. 5 degrees of freedom and alpha of 0.05. So here, and of course that's off our table here, so we're going to have to look in the textbook. So table A4 in our textbook, it's actually on page A9, but it is table A4. We find alpha. We're looking here, we've got the 0.05 on top, 5 degrees of freedom on the side, and we follow them over. And we get a critical value there is 11.070, which is what they gave us here. Now our test statistic of 9.4 is not bigger than that critical value. Since our test statistic is less than the critical value, we fail to reject. So our conclusion is there is not enough evidence to conclude that the die is not fair. That doesn't mean the die was fair. There just was not enough evidence to conclude that it wasn't. Now, if I wanted to use the table to find the p-value, it's really tough. I would look at my table, and I'd be looking along that row for 5 degrees of freedom, and I would find the number closest to 9.4. And as I do that, I have a 9.236, which isn't far away. That's under the alpha of 0.10. So we know our p-value is slightly less than 0.10 because our test statistic is a little bit more than the 9.236. One of the advantages of the calculator is it'll give us that exact p-value. Unfortunately, it does not find the critical value. And our calculator does not have a chi-squared inverse, so we cannot enter in alpha and our degrees of freedom and get a critical value off the calculator. It's not a function that it has on it. You might be able to download that function somewhere, but it's not built into our calculator. Okay, so let's look at our calculator and how we would enter this. The biggest thing we need is just off here, the observed is going to be in our first list and the expected in our second list. To do the goodness of fit on the calculator, we use the list. So we're going to go to Stat and Edit. And in list 1, we are going to put, let's clear out my list here. Just clearing them out so we've got a clean slate to work on here. Then in list 1, we're going to put in our data. I'm not going to put in the category, but I'm going to put in the observed values in list 1 here. So we have 12, 7, 14, 15, 4, and 8. Then in list 2, I'm going to put in the expected values. They're all 10. So I've got them all entered in. So I'm going to exit out of there. I'm going to do Stat, Tests. This is a chi-squared goodness of fit. Now the observed, I want to switch that to L1, so I'm going to do second 1 for L1. The expected's in L2, so second 2 for L2. Degrees of freedom here are 5. That was set correctly. And we're going to hit calculate. And we get the same test statistic of 9.4, and we get a p-value. As we had said, we expected the p-value to be just under 0.10, and it is 0.0941, which is exactly what we had here. So the way we would do it here is we would use a p-value test. Since alpha is 0.05, We would reject if the p-value is less than alpha. Here, the p-value is not less than 0.05, so we do not reject. We fail to reject that null hypothesis. Once again, there is not strong enough evidence to conclude that the die is not fair. So we found the critical values of chi-squared, and we performed the goodness of fit test. Now I'm going to take a quick little jump over to Excel here. And in Excel, there's actually a chi-squared inverse function. So remember, we had alpha of 0.05, and we had 5 degrees of freedom, 6 minus 1. So what I can do is hit equals chi, I type in chi, and then I'm just going to select the chi-squared inverse here. First is the probability. Now, we can't put in 0.05, because remember, that's a right tail probability. And Excel always looks at the left tail. So if it's 0.05 in the right tail, 1 minus 0.05 is 0.95 in the left tail. Or think of it as 5% in the right tail, 95% in the left tail. Our degrees of freedom are 5. Hit enter. And there we go. That is actually the critical value that we had before that we used. Now we look back here, remember we found 11.07 was our critical value. So that finds that critical value for us. So here, if we're looking at the values on our die, and let's do our observed values. 12, 7, 14, 15, 4, and 8. Just to double check, I'm going to put a sum in there just to make sure that's 60. And it is. Our expected is going to be 10 for all of them. You can see that's a sum of 60 as well. So then we'll do our test statistic. For each value. So we're going to hit equals. In parentheses, it's going to be observed minus expected, close parentheses, squared. Now it's shift 6 to get the little caret squared, then divided by the expected. And I get that 0.4. And I can just fill that command down, and you can see I get the contributors for each. And I can do a sum down here. And there is my value, my test statistic. So, again, since the test statistic of 9.4 is not greater than the critical value of 11.071070, we fail to reject the null hypothesis, H0. So it's pretty easy just to plug this into Excel. Excel has that added advantage. It's one of the few things that Excel does better than the calculator. It actually has that chi-squared inverse. So next we're going to pop back to our PowerPoints and we're going to look at our tests of independence. Okay, so we're looking at the test of independence. Like I said, we're looking at a contingency table where we've got one set of data but two different treatments or two different sets of variables that we're splitting it up amongst. So first thing we're going to do is look at interpreting a contingency table. Then we're going to perform the test of independence, and then the test for homogeneity is actually slightly different. I'll show you how that works. So interpret the contingency table. As I said, a contingency table here, we're looking at one set of data, but we're breaking it up amongst two different variables. So we got hours studied per week, 0 to 10, 11 to 20. Technically that should be like 10.1 to 20, but we're rounding the nearest hour, and then more than 20. And then their major classification, not specific major, but major in humanities, social sciences, business, or engineering. And we're looking at their hours studied, per week compared to their major. And what we're trying to test here is, does the major that the student is in change affect the number of hours a week that they study? Is there a relationship, or are they independent? And our null hypothesis is always going to be that they are independent. So H0 is going to be they're independent. And we can word it a little bit more eloquently than that, but then H1 is going to be not independent. So there is an indication that the variables are not totally independent of each other. So let's take a look of what we're going to do. Now here, again, it's often easiest, and what we will do is we're going to do row totals and column totals just like we did for a probability. So this is going to be the row totals here. We'll put those three in there, and then column totals. For each column. And then there is going to be that grand total here again that better add up in both directions because we have the same total no matter which way we're adding them up. So that's our contingency tables from before when we did those when we did probability. So now let's look at actually performing that test of independence. So in the previous contingency table, we are interested in determining whether the distribution of one variable differs depending on the value of the other variable. So that would say the variables are dependent. If the distribution of one variable is the same for all values of the other variable, in other words, the value of the other variable does not affect the distribution of the one variable, then the variables are independent. So let's take a look then at this data on the number of hours studied compared to their major. So our null hypothesis is that they're independent, as I said, worded it a little more eloquently, saying hours studied and the major are independent. And then, of course, the alternative, H1, is that the hours studied and major are not independent. So we will use a chi-squared goodness or a test for independence here to test to see if that is true. So we look at finding our expected values here. And what we're doing is we're actually looking at doing kind of like an expected value from the row and column probabilities. Let's go back up to this contingency table here quick. You know, the probability in this table of studying 0 to 10 hours is this row total divided by the grand total. So that's the probability. Now, the probability, given that you're in humanities, should be the same. So the number here should be this total of humanities majors times that probability, that proportion. So that's how we're finding the expected values. We're taking the row total divided by the grand total and then times the column total. Row total divided by grand total times the column total. Now, often we shorten that and we just do this. Row total times column total over grand total, like that. So that's basically what they're hinting at down here, is that probability of studying 0 to 10 hours times the frequency of the humanity majors, or the other way around, of the frequency of studying 0 to 10 hours times the probability of being a humanities major. So you can see here they're looking at the row total, and they're kind of expanding this out. Here they did the row probability, which is the row total divided by the column total, by the grand total. They did the column probability, which is the column total divided by the grand total, then multiplied by the grand total. Well, one of those cancels out, and we have row times column divided by the grand total, which you can see is what we get here, giving us that 88.665 frequency. And there they're just formalizing that. The expected value for each is the row total that it's in times the column total it's in divided by the grand total. We have to do that for every cell in that table. So our hypothesis testing procedure is to create our hypotheses, the null and the alternative, as we did, compute row and column totals, as we've done, as we stated, then compute the expected frequencies. Again, row total times column total divided by grand total. And then we do the test statistic. It's going to be exactly the same as it was for the test for goodness of fit. It's the observed value minus the expected value. That difference is squared and then divided by the expected value. And you'll get that test statistic for each cell in the table. We add them all up to get the overall test statistic. For the critical value, we need the degrees of freedom. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Well, this had 3 rows and 4 columns. So 3 minus 1 is 2. 4 minus 1 is 3, so 2 times 3 is 6. This should be 6 degrees of freedom here. And then just like with the goodness of fit, if our test statistic is greater than or equal to the critical value, we would reject HO. Otherwise, we would fail to reject it. So here's our table again. Here they just show we found the row total. 68 plus 106 plus 131 plus 40 is 345. All the way down, found the row totals. Then the column totals, 68 plus 119 plus 70 is 257. So we did that all the way. The grand total was 1,000 students that we surveyed. So then we found the expected value for humanities and 10 hours a week. Took the 345 times 257 divided by 1,000. That gave us the expected value there, which turned out to be the 88.665. And we did that for each one of these. So now we add those all up and we get 34.638 is our test statistic. Well, what was our critical value? Well, we had 6 degrees of freedom. Did we state alpha here? Alpha we said was 0.01. I didn't catch that earlier. So we're looking in that table in the book again. 6 degrees of freedom and a right tail region of 0.01 is going to be 16.812 it looks like. And that's what they're given here is 16.812. 34, our test statistic of 34.638 is greater than that critical value of 16.812. Therefore, we reject HO. So here we conclude that the choice of major and the number of hours spent studying are not independent. It looks like the number of hours studied varies depending on the major. How would we enter this in the graphing calculator? Well, in the graphing calculator, since the contingency table is two-dimensional, we cannot just use the list. We're going to end up using the matrix function. So we're going to define a matrix. I'm actually going to go one more step here, so I got everything in front of me. So we're going to go to the calculator. We'll clear this off. We're going to go matrix. So second matrix is right here above the x negative 1. Brings us to the matrix menu. We're going to go to edit. Select the first one. This is rows by columns. There are 3 rows and 4 columns. So this is a 3 by 4 matrix. So 3 by 4. The first number is going to be 68. That's just this number here. The next cell is 106. It goes horizontally. Then we have the 131. And the last number in the first row is the 40. Second row, we have 119. We have 103. 127. And the last number in the second row is 81. And finally, in our third row, we have 70. 52. 51. And 52. So we've got the table filled, or matrix filled out. So I'm going to second quit to get out of there. And now I'm going to go back into that matrix menu again. Go over to edit. And I'm going to select matrix B to edit this time. And what I have to do is I have to dimension matrix B to be the same dimension, 3 by 4. and I have to zero it all out. This one already has all zeros in it. If it wasn't, I'd have to go through and delete every number or put zeros in for every number so that matrix was filled with zeros. What I'm doing that for is I'm setting up a blank matrix, and the calculator is going to put those expected values in there for us. So I quit to get out of there. Now we're stat tests. This is chi-squared test. They just call it test. They don't call it, test of independence or anything like that. So we select the chi-squared test. It's actually the observed values are in matrix A, so that's there. If it wasn't the right one, what we would have to do is do second matrix. And from the names list, we would select the first one. Here's matrix A. Then put the name of matrix A in there. Hit enter. Expected is in matrix B, so that's correct. Again, you do the same thing if you needed to change that name there. We're going to select calculate, and there we go. We get a test statistic of 34.637, which is what we had here. 34.638 when we rounded it off. And a p-value of, that's to 10 to the negative 6 there. So what that means is that is, let me get my pen going here. 10 to the negative 6 means the decimal point has to go 6 spots to the left. So that is 0.12345 zeros. And then 50 will go 6. So that is obviously less than our alpha of 0.01. So therefore, again, we definitely will reject the null hypothesis and conclude there is a relationship between the number of hours studied and the major. Or the number of hours studied does vary by major. Okay, now before we do the test of homogeneity, I'm going to jump over to Excel here, and I'm going to do this test on Excel. So again, we're looking at hours studied. And we're going to do majors, humanities, social science, business and engineering, and then our hours studied 0 to 10, 11 to 20, and more than 20. I'm just going to put more 20 because I don't have room there, but that's fine. So then we have 68, 106, 131, 40. 68, 106, 131, and 40. Kind of surprised I remembered all those. 119, 103, 127, and 81. 119, 103, 127, and 81. 70, 52, 51, 52. So let's look at the totals here. Column totals. I'm going to find the sum. Copy those over. Now I'm going to go one extra here for the grand total. This is going to be the row total. Sum those up. And run it down. It does give us 1,000, so we're good there. I'm just going to bold those so I know their totals are not really part of the data. Now I'm going to put, this is my observed values up here. I'm going to put another table down here for my expected values. So for let me just copy these. Really don't need the totals. I'm going to get rid of those. So it's going to go in here is this row total times this column total divided by the grand total of 1,000. I'm just going to type that in. And here I'm going to do that should give me my expected values there. That should give me my expected values here. And my expected values here, just using the Excel functions. So you can see what I did here is G22, that row total, oops, G22 is my row total, times C25, which is my column total, divided by the 1,000, my grand total. Here, G22 is my row total, divided by D25 is my column total, divided by my grand total. And just for each one, you know, this one, I did G23, which is my row total, times D25 is my column total, divided by the grand total. Here, it should be this one, so that would be G24, which is what it is, times E25, and divided by my grand total. So now all I have to do is I have to add all those up. So I'm going to sum these. Oops, sorry, not adding those up yet. I need to now calculate my test statistics. So for each one here, it's going to equal my observed minus my expected squared divided by my expected. And those are all my test statistics. So they just fill over for those. I don't have to adjust anything. Up here I had to adjust. Notice I had to put in the dollar sign so that when I move cells, it didn't move automatically. So now I'm just going to find my sum of these four. Fill it down. I'm going to sum that. Sum only goes one dimension. It doesn't allow you to sum a whole box like that in Excel. So you have to sum the rows and then add them up. And we do get the 34.637, which is what we had here as our test statistic, 34.6377. So in Excel, now remember we had 6 degrees of freedom and alpha of 0.01. So we do that chi-squared inverse here. Now remember again, 0.01 is the right tail probability. So the left tail probability would be 0.99, 6 degrees of freedom, giving us a critical value of chi-squared of 16.811, which is not what we had here. Oh, we did have 16.811, so it is the same. I was thinking of 17 for some reason. So it is 16.812 actually if we rounded it off. So here, since the test statistic of 34.6378 is greater than the critical value of 16.8119, we will reject H0. There, get that to where we can see it. Now let's look at the p-value. Can we find the p-value from this? Well, yeah, we can find our chi-squared distribution here. X is going to be this value, the test statistic. The degrees of freedom are 6. The cumulative is true. And of course, the p-value is actually, this is giving us the left tail probability. So our p-value is always going to be 1 minus that. So this is going to equal 1 minus what we calculated there with the chi-squared probability. There it is, exactly the same p-value we had on the calculator. Okay, so let's go back here now and let's get to that test of homogeneity. Our difference in the test for independence and the test for homogeneity is actually quite subtle, and it's all about how we put the data in the table, how we select the data from the table. What we did up above here was we took 1,000 students, period. And then we set them in the table according to their major and their hour studied. We did not separate them out before we selected them. So we were selecting from one population. So test of independence, we were selecting from one population. And then splitting it up under two different variables. For a test homogeneity, we divide them up first. So what we would do in a test for homogeneity is we might say, okay, we're going to look at these 4 different majors, and then we're going to select 200 people from each major. So in this essence, what you're doing is now you're defining 4 separate populations, and you're selecting samples from each of 4 different populations. And that's basically the definition here for our test. You know, contingency table so far, the individuals were from a single population, and then they were put into both rows and columns as they were randomly selected. But in some cases, the investigator will assign them to their row or column. So therefore, it's not random anymore. So they're chosen to be within that specific row or that column. And then only one of the rows is really a variable. So in these cases, we consider the rows as representing separate populations. So they're saying we separated them by rows and then placed them in the columns as we gathered the data. We're interested in testing the hypothesis that the distribution of the column variable is the same as the row for each row. So this is homogeneity. So very slight difference there. So here, we're looking at different drugs, telmisartan, ramipril, and then a combination of the 2 drugs together are designed to reduce high blood pressure. So we're doing clinical trials. So we've got patients have been assigned one drug or the other or a combination of the 2. Then they actually test. Did they have a fatal heart attack, a non-fatal heart attack, or no heart attack at all? So in this experiment, the patients were assigned to a row. We randomly chose patients to be on telmisartan. Sorry, I have a hard time pronouncing that. Telmisartan or ramipril, or the combination of both drugs. So what we've done is essentially created 3 different populations, and we're gathering the same data from all 3 populations, but it is 3 separate populations. We just didn't randomly select people and divide them by what drug they were on and what conditions resulted. From here on out, this is exactly the test is exactly the same as the test for independence. So we have to find row and column totals. We have to find our significance level. This is 3 rows, 3 columns, so that's 2 by 2. Let me write that out. 3 rows, 3 columns. So it's 3 minus 1 by 3 minus 1, or 2 by 2, so 4 degrees of freedom. Alpha 0.05 we're defining. So again, we have to do the rows and the column totals, just like we did before. Column totals, row totals, grand total. Then the expected values are found by doing, so we did here, row total times column total divided by grand total. That first row total is 8542, first column total is 1821, and the grand total is 2560, or 25620. That's exactly what we did here to get that first expected value for the first cell in our table here, right here. Do the same for the rest of them. We do observed minus expected squared, and then divided by expected for each cell in the table. Add them all up. Here we get a test statistic of 2.259. Now that's pretty small. I can almost guarantee you that's going to be too small to reject, but let's find our critical value. As we said, there's 4 degrees of freedom. We use that table on A4, alpha of 0.05, 4 degrees of freedom, we get 9.488 is the critical value. So again, since our test statistic of 2.259 is not greater than the 9.488, in fact, it's less than the 9.488, we fail to reject, or we do not reject the null hypothesis. So therefore, there is not enough evidence to conclude that the distribution of outcomes is different for each treatment. So we can't conclude there's any difference. So here we interpreted the contingency tables. We did a test for independence and a test for homogeneity. And remember that very slight difference in the test for independence and homogeneity are simply in how the data is chosen and then arranged. Once it's in the contingency table itself, the mechanics of the test is the same for both. So I'm not going to show the calculator example for homogeneity or Excel because it should be pretty obvious. It's the same keystrokes, you just got to get the data table in there. So that is it for our chi-squared test. I'm going to leave it there. If you guys have any questions, please let me know. Otherwise, you have a great week.